Chapter 1-6. I printed off your notes for you. You're going to have to add a couple things throughout. Okay, so here we go. The one-to-one function. Now, remember whenever we talked about being a function, I talked about ice cream or candy examples. Remember that? I said here and here one's ice cream, here and here one's candy. You can't choose both because if you choose both, that means that you're not a function. Remember we talked about that. Okay? Well, today we're talking about one-to-one functions, which means now, to be a function, you have to choose one y value. To be a one-to-one function, not only does the x have to choose one y value, but the y value has to choose one x value. Remember previously I said who in here wants ice cream, and then a whole bunch of people raised their hand? Was that a legal function? Yes, because everybody can choose to have ice cream if they want. That made it a function, but to make it a one-to-one function, we have to be a little bit more precise. What do I mean by that? Jenna, what's your favorite ice cream? Waffle cone, like caramel ice cream, caramel and the chocolate cone waffle pieces. Okay, well that means to be a one-to-one function, that means that nobody else can eat from the tub of the waffle, caramel, whatever, ice cream. Does that make sense? Hold on, your favorite.
Vanilla, we'll go with that.
That means nobody in here can have vanilla. That's his tub and his tub of ice cream only. That's what it means to be a one-to-one function. Do we understand that? Once somebody has chosen, vanilla maps to him and he maps to vanilla. Does that make sense? Okay? Now, a one-to-one function says a function f of x is one-to-one if every element in the range is paired with exactly one element in the domain. Now, I give you this lovely little function, y equals the absolute value of x plus 1. What's the absolute value look like? A b, right? Now, is this a function?
Yes.
In other words, did every x value choose one y value? 2 chose 3, 1 chose 2, 0 chose 1, -1 chose 3, -2 chose 3. Is that legal? Sorry. Yes, it's a function. We good?
Yes.
Now, is it a one-to-one function?
No.
Why is it not a one-to-one function?
That's 2 with negative.
Because 3 is being chosen by both 2 and -2. Is that legal?
No.
No, it is not a one-to-one function. What is the domain of this function? So -2, -1, 0, 1, 2. Why did I write it differently than what you just said? You said from -2 to 2, implying that I'd have -2, -1.5, -1 3/4. Is that in there? No. There are only 5 domain values there. Do we understand that? Yes or no? So whenever you're doing domain on a set like this, you need to be very careful. Which range? Do we all understand that, yay or nay?
How is it a function?
How is it a function? It is a function because every one of the x values chose one y value. 2 only chose 3. 1 only chose 2. 0 only chose 1.
Oh, okay.
-1 only chose 2. And -2 only chose 3.
Okay.
Does that make sense? Okay?
Dollars.
Dollars. Okay. Now, dollars. Are we good on this? Now, the next thing I left a blank. It's not on your paper, but you need to just go ahead and tack this on the bottom of that. Was we talked about the vertical line test. A vertical line test determines what?
Function.
If it's a function. Is it a function or not? So remember, whenever I had something that looks like this, I went ahead and said, is this a function? Well, in order to determine if it was a function, I had to pass the vertical line test. If it intersected it more than one time, it was not a function. Does this cross more than one time? So is it a function? Yes, it is. Well, just like we had a vertical line test to determine if something's a function, we also have another line test to determine if it's a one-to-one function. Anybody know what that is? The horizontal line test. The horizontal line test is a function y equals f of x is one-to-one if and only if IFF. Do you understand that? IFF. And
No, it's not.
A function y equals f of x is one-to-one if and only if no horizontal line intersects the graph in more than one point. For example, we just talked about this lovely little parabola graph. Yes? Is this a function?
Yeah.
Is it a function, meaning it passes the vertical line test?
Yes.
Yes. Is it a one-to-one function?
No.
No, it is not a one-to-one function, because look, what this means is these two people, and whenever I talk about the horizontal line test, I'm going to use the yardstick. All these numbers, the inches on here, are people. Okay? When it crosses right here, those two people chose the same exact ice cream container. Are they allowed to choose the same ice cream container?
No.
No, we're greedy people on one-to-one functions, and we don't want to share out of our tub. You understand? Okay? So this is not a one-to-one function. Now, why is this important? Because what we like to do with one-to-one functions is we like to find inverses. We like to find inverses. If you are a one-to-one function, then you have an inverse. Do we understand that? Now talk to me about this. Can I make any function become a one-to-one function? Can I make the parabola x squared become a one-to-one function? I'm sorry?
Yes.
How? Yes, I have no idea. Can I restrict something? That's exactly what you need to do. What he just said is, can you restrict where everything crosses twice? So if I wanted to talk about this, where would I restrict so that it only crosses one time? Everything above where it changes direction, meaning the vertex. Everything to the left of the vertex or everything to the right of the vertex. You can't have both of them. So in this case, I can have y is equal to x squared if I say x can be less than or equal to 0, or x is greater than or equal to 0. Because what that means is I am essentially taking only one side of the parabola. Do we see that? I'm taking one arm of the parabola. In this case, this is going to be y is equal to x squared, where x is greater than or equal to 0. The other side, and I'll make that in green, would be y is equal to x squared when x is less than or equal to 0. Do we understand that that would be a one-to-one function? The green by itself, the red by itself. Do we get that, yay or nay? What I've done is put a domain restriction on that. Any questions over that? Perfect. Now, I want to backtrack for one moment, and we talked about inverses. Now, what happens if I were to give you a set or a set of ordered pairs? If I'm giving you a set of ordered pairs, I want to know, how do I determine the inverse? Well, now, what did I just talk about with inverses before? Inverses undo each other. Addition undoes subtraction, multiplication undoes division. So if I want to find the inverse of a set of ordered pairs, what do you think we need to do? What am I given when I have an ordered pair? A point, which is domain and range. Well, what undoes domain? What undoes range? So what you're telling me is that these would what? The inverse would be flip-flop. So 2 goes to 1, 6 would go to 5, and 10 goes to 8. Now this is very important whenever we're trying to find graphically a picture of an inverse. And we're going to talk about that when we get to your homework in a little bit. But I just wanted to make sure that you had this on in your notes that you could refer to it tonight. Now, with that said, we have these inverse characteristics. Now you need to add number 5 to this. So number 1, f of x must be a one-to-one function to have an inverse. If it's not a one-to-one function, you don't have an inverse. Which means, how do I determine if it's a one-to-one function? Number 2, it must pass the horizontal line test. If it doesn't pass the horizontal line test, it's not a one-to-one function, which means it does not have an inverse. Number 3, the inverse of f of x is denoted as f to the negative 1 of x. F to the negative 1 is not the negative exponent. It indicates inverse notation. Am I clear? Number 4, f of x and f inverse of x must be reflected over reflections of each other over the line y equals x. Why would it be reflections over each other over the line y equals x? Because number 5, if the two functions are inverses, then the composition of the two functions will equal x. Number 5 is not written down in your notes or your handout. You need to make sure you write number 5 down. What am I talking about whenever I talk about this? I'm talking about f of f inverse of x has to equal x, and f inverse of f of x has to equal x. That's what I'm talking about whenever I'm talking composition. You ready? Okay. Now, how do we find an inverse? First thing you want to do is you want to get rid of function notation. What is function notation? F of x, g of x, h of x. You with me? That's that formal notation. And what you want to replace f of x with is going to be your lovely little y equals. Okay? So if you see f of x equals, replace it with y equals. Why am I wanting you to replace it with y equals? Because what you're going to do to find the inverse is you're going to switch x and y. Step 3, then you're going to solve for y. In step 4, you're going to replace y with f inverse of x. And then we're going to find, this is an example right here. Now, why did I tell you to swap x and y? Because you're swapping the domain and the range. That's what it means to be an inverse. To be an inverse, you're swapping the domain and the range. Do we understand that, yes or no? So does everybody understand why we're swapping x and y? To get the inverse. Now, first of all, I want to know, without graphing this thing, f of x equals 3x plus 2 is what parent function? What is the parent function to f of x equals 3x plus 2? The parent function is going to be x. Do we understand that? In other words, we're talking in the form of mx plus b here. What is mx plus b? An equation of a line. And tell me, an equation of a line either goes uphill or downhill, correct? Does that pass the vertical line test to be a function? Well, here's my yardstick. This is a line. And we're going uphill, which means it has to look like this, right? So does that pass the vertical line test? It does. Does it pass the horizontal line test? Yes. So what does that mean? It's a one-to-one function, which would imply what? It has an inverse. Notice I looked at the parent function. I didn't have to look at it graphically on in the calculator. I could do that all based upon what we just learned in last section about parent functions. Yes? So I know this thing has an inverse. So how do I find it? Step 1, what do I do? Get rid of function notation. So what do I do? Y equals 3x plus 2. Step 2. Swap x and y. So this is x is equal to 3y plus 2. Step 3. Solve for y. So I'm going to subtract x and then divide by 3. And then step 4. I'm subtracting 2. Did I say subtract x? Forgiveness, please. I asked for it. I said the wrong thing, but I did the right thing. Do I get any points for that? Okay. Okay, so what do I do? F inverse of x is equal to x minus 2 over 3. That is your inverse. Do we understand that? Because you're denoting it, you're showing that that is an inverse by simply writing it as f inverse, referring to the function f and saying that f inverse is that. Yes, you can write this as 1/3 x minus 2/3 if you wanted this to be in y because of x plus 2 form. Absolutely, they're the same exact thing. Depends upon how you want to word it. Okay. Now I want to graph this for you on the graphic calculator because I want to show you something very special.
Do we have to write like the blue?
No, you can write it either way. Okay, so if I graph this, my original function was 3x plus 2. There's my original function. My next function is going to be x minus 2 over Okay, syntax error. Thank you very much. Why do you have 2 equal signs? Didn't like me. I know. It doesn't want me to delete the first one. Okay, so I have x minus 2 over 3. Was that the inverse of the? Okay, those are my 2 functions. Now I'm going to graph a third function, and that third function is going to be y equals x. And what I'm going to do is I'm going to make this line dotted. Yes, your calculators do this. I know. Okay? Now, what I want you to notice here is that dotted line is the line that you would fold on. Just like in grade school when you cut on the dotted line, I want you to fold on that dotted line. And what happens to the red part of this, the top part of the red graph? It's going to reflect and lie directly on what? The green part. And what's going to happen to the green part of this graph? It's going to flip over to the red part of this graph. Do you see that they are reflections of each other with the line y equals x? Yes or no? Okay? Now what I also want you to notice is that if I hit Control-T for table, okay, f1 is 3x plus 2, f2, the green function, is over here. Now, if I am at -2, I get -4, right? So what is going to happen at -4? And you can't see that, so let me. So do you see at -2 it was -4 on my f function, but on my inverse function at -4 it was -2. What do you notice? Your domains and your ranges swap. Do we see that, yes or no? Okay? And you can do that with every ordered pair. Jenna? This is just another point. This is -7, this is going to be -1 2/3. So at -1 2/3, it would be the point -7 over here. Okay? At -1, I'm at -1, at -1, -1. It's the same point. Okay? But the point is that you can see that they're going to be reflections of each other over that. Okay? Now the next thing you need to know is to find the inverse of x plus 1 over 2. Now, does this have an inverse? Some of you are not certain. You're kind of like, I'm just going to try to find it. What is the parent function? The parent function is still x, so does an x have a inverse? Yes, it does. So now that I know it, I'm going to have y is equal to x plus 1 over 2. And what do? Come on. Switch them. So that's going to be x is equal to y plus 1 over 2. What do? Multiply by 2, so 2x is equal to y plus 1. Now what? 2x minus 1 is equal to f inverse, and I just skipped that step right there so that we could get straight to it.
How do you know which parent functions have an inverse?
Very good. Which parent functions have an inverse? Well, let's talk about that a minute. If I give you y is equal to x squared, that's a parent function, correct? Does this, it looks like this, according to last section, does that pass the horizontal line test? No, so does that have an inverse? No, the only way it can have an inverse is if I restrict the domain. Does that make sense? Does this, y equals x cubed, which looks like spaghetti, does that have an inverse? Yes, because it passes the horizontal line test. Matt, does this have an inverse? How do you know? What does it look like? Huh? Pay attention. You're trying to doze on me over there.
No, I'm trying to figure out the last one.
Alec, what does this look like? It's my one-armed bandit. So if this is my one-armed bandit, does this have an inverse?
Yes.
It does. Now, some of you are sitting here saying, doesn't it level off and get to be the same value? It does not. When we draw one-handed like that and we sketch things, it appears one way, but it's really not. So if I graph this thing and I do the square root of x, do we see that? Now, how do I know that it continues off? Well, what can you always look at? The table, Control-T. What's happening to y as x gets big? It's getting bigger, so it's gradually getting bigger and bigger and bigger and bigger and bigger. Clear out there in space. Do we see that? So does it have is it a one-to-one function? Yes, it is. So this is going to have an inverse. Do we all understand now how to use your parent functions to help you if something is one-to-one? Yes? Excellent. Moving right along. Verify that the function g of x is the inverse of f of x. Verify that the function g of x is the inverse of f of x. How do I verify if two functions are inverses? Well, you can find the inverse of each one. Oh, thank you. The last step tells us to compare the compositions. What should the compositions always equal? This is number 5 that you wrote down. Compositions should always equal x. Therefore, I'm going to do f at g, which is going to be x plus 1 over 2. So that means I have 2x minus 1, and I'm going to plug in for x, this. The 2's cancel out, and I'm left with x plus 1 minus 1. Those cancel out, and I'm left with x. Is that what I wanted it to equal? Absolutely. And then over here, I'm going to do g at 2x minus 1. And g is going to be x plus 1 over 2. So that's 2x minus 1 plus 1 all over 2. Those cancel out. And I'm left with x. Do those two things equal? Yes. Now listen up a minute. Tonight's homework is very simple. What do I want you to do? I want you to tell me 1 through 6. Is it one-to-one? Yes or no? If it is one-to-one, find the inverse. Problem 7 through 10. I want you to prove that f of x is equal to g of x. And then 11 through 14, find the inverse and then prove one of them. You don't have to do both, f of g or g of x. And then matching is 15 through 18. Find a point and then find the inverse of it. Have a great day.